All right, it's me again. We're in our 7th week on this. Exciting. Here are some of the things we looked at. We looked at this guy shivering. There were a couple people shivering. We saw a balloon exploding, meat tenderizer, hot cold packs. Some of the things that people said about these were duckies, shivering, breathing, machine, water, hot pack, cold pack, shivering. Some of the questions: how does shivering affect breathing? Does breathing shallowly make you get cold faster? What is the unstable explosive used for? What's in a hot pack? How to use a cold pack? What does a tenderizer do? What does a cold pack do? Why does the hot pack turn hot? So we have these that we can go through. So if we go to the first one, remember we talked about the shivering affect breathing. So I'm cold, and I'm shivering, right? I'm shivering. And so when I'm shivering, or let's say it's cold outside and we show up outside, Garrison and I, to throw the football, and it's cold outside, I'm wearing a jacket. And then we throw the football for about 20 minutes. We start to heat up, and then we strip off the jacket. Now we're down to a t-shirt, even though it's 30 degrees outside. Why is that? It's the same reason you shiver. When you physically move, when you're physically moving around, you're generating heat from your body. That's why you get under the covers at night and maybe go, and you move around real fast, because you're trying to generate heat through your body. And here's a little known fact: 7% of the energy used to move your body around is lost as heat. 7%. There's the story about the guy who survived overnight by climbing a tree and sliding back down, but by generating heat. And so how does shivering affect breathing? When you shiver, you're moving around, and the reason you're shivering is your body is generating heat by contracting your muscles. It's contracting, relaxing, contracting, relaxing, contracting, relaxing, and 7% of that is lost as heat, which then helps keep you warm. And so remember when we said we start with glucose, we eat the sugar, and then it goes through these various little steps here, and then we end up with that little thing called ATP, which was energy. But then we also needed to use this oxygen right there. The more glucose you burn, the faster you're moving around, the more oxygen you're going to burn. So, does shivering affect breathing? Yes. It does, because you increase the metabolic rate. You increase the metabolic rate, and that's due to shivering, which means you need more oxygen. So the more shivering you do, the more breathing you do, because of that one little oxygen right there. Does shallow breathing make you cold faster? No, because breathing should mean your metabolism is moving faster, which should make you warm up. So does breathing shallowly make you get cold faster? No is the answer to that second one. And why? Because breathing more should mean that your metabolism is moving faster, not slower, which would make you cold. So if we tie this into the next one, which is, what is the unstable explosion used for? So you remember this balloon right here, it just barely touched that table, and boom, it went right off. What that means is that the reaction occurred spontaneously. It really didn't take much for it to go off. It barely touched the table, and boom, it went off. Whereas sometimes fireworks, you have to add heat to it. You have to do things to make that thing happen. But this happened spontaneously. And so This happens spontaneously, and then this explosion happens, and this stuff explodes out. And when heat is given off, it's called an exo, meaning outside, thermic. So heat's given off, exothermic. And it didn't require any energy to make that thing go boom. So if we look at this, here is maybe A is equal to the balloon and B is equal to the blown up balloon. See that right there? A and B. And so A is the balloon, and then it barely touches the table, and then boom. And so it gives off all this energy, you know, and we could say he gives off this much energy right here. And then boom, you know, it explodes as an exothermic reaction, right? Now if we consider the same balloon, except now it's filled with air. And then in order to pop that balloon, we can bounce it on the table, it doesn't do anything. We can bounce it off of our heads, it doesn't do anything. But then we start squeezing it. We squeeze it right here, and you probably feel the balloon starts to get warm. You know, under your hand, the more you squeeze it, warm. And so then what you're doing is you're adding warmth to it, you're adding heat to it, you're adding energy to it. You squeeze it, and then we get the explosion, right? And so we're adding energy here. And so that might look something like this. And so then the amount of energy that we have to add is right here. And that gets us from A to B. So we're adding energy to go from A to B. Now I should maybe explain that A to B could be a full balloon to an empty balloon, or this could be any kind of reaction. You know, if you mix salts and waters together, it's going from salt plus water to salt water. So it could be like mixing two things and then what you end up with. And so sometimes things take in energy and sometimes they give off energy. And so some reactions, like we saw, are exothermic, like an explosion, and other times you have to add energy, and so we can call those, let's just call it endothermic. And two real-life examples of this are hot packs and cold packs. And so if we were to put exothermic and endothermic where would we point those to? So which one is exo and gives off heat? That would be this one. It's giving off heat. Whereas the endothermic one, it's taking in heat and energy in order to go from, say, room temperature to cold. And this is going from room temperature to hot. And so you open the packet up, you shake the hand warmer. All that's doing is getting oxygen in there, and it goes from room temperature, and whatever chemical reaction is happening in there, it's an exothermic reaction, and it's giving off heat, and that's what makes your hands warm. Whereas the endothermic reaction, is taking heat from the outside and using it for the chemical reaction, and by drawing in heat from its surroundings makes it cold. Got that? So we have the exothermic reaction, gives off energy. Endothermic reaction is taking energy from its environment, which then makes the thing cold. And so now if we go back and look at this glucose to energy, so then we shiver, and we need a lot of this energy. 7% is lost as heat. But if you look at, this goes from here, look, it goes from glucose, it doesn't matter, but these are cool words. Then it goes to from glucose to pyruvate. So those are just two chemicals. And then the pyruvate gets changed to acetyl-CoA. And then it goes through this thing, and then eventually it becomes ATP. So this is just like going from A to B to C to D, up to D to E to F. Each one of these things is a chemical reaction. And both exothermic and endothermic reactions are used throughout all of this. So the two kinds of reactions, exothermic and endothermic, both of them are used to move this sugar and turn it into different stuff till we can finally use the energy. So pretty cool. So if we were to then look at, we go from A to B, and sometimes it takes a considerable amount of energy to do that. But one way that we can make this line, because this is how much energy it takes to do this thing, right? And it would be way better if it was, flat, like the spontaneous balloon, But we can do things to go to make it like this, and those things are called enzymes. So all that an enzyme is something to make the reaction happen faster. The reaction to go from A to B, from B to C, from C to D, D to E. You use enzymes to make that go faster. And the way it does that is it reduces the need for all the rest of this energy. And an enzyme does that. And so enzymes are pretty important things because they happen in a lot of different things. But an example of an enzyme is a meat tenderizer. This is made from pineapple. I just butchered that word. Pineapple, papaya. But you can also take, a freshly killed deer. And you might use a meat tenderizer to make it tender. Or you might hang it. Or a third way, you can use an enzyme, which is a meat tenderizer. And our A to B, this is the A, is maybe this guy, fresh. B is we want it to be tenderized. And so how do we go from A to B? We can pulverize it. We can let it hang, which takes longer. Or we can use a tenderizer. And a tenderizer will speed up the breakdown as we go from A to B. So pretty cool. So now let's connect what we learned to me. Connecting me to the information. I get cold. I shiver. And I warm up due to exothermic reactions happening in my body. And me capturing 7% of that heat that's left off. I use enzymes millions of times a day to make my reactions go faster, whether it's cellular metabolic rates or anything. Enzymes make A to B way easier by making how much energy you have to add to it to a lot less. I use heat pads when I get cold. I give them to my kids. And so what a heat pad is a chemical reaction. And it's an exothermic chemical reaction. I also use cold pads to cool. For judo, somebody gets hurt, bruised, we crush up a cold pack, and it is an endothermic reaction which causes it to get cold. That's a blue line if you can't see. And then enzymes can also be used, as we said, to go from A to B. And this could be fresh meat to tenderized. And we can use that in a variety of different ways. So that is all, folks.